Introduction and the Origins of Cosmic Curiosity, Humans and the Stars. A 5,000-year journey of wonder since ancient times, the night sky has mesmerized us. More than 5,000 years ago, our ancestors in Mesopotamia, Egypt, and later in Greece looked upward and saw more than just twinkling stars. They saw mystery, order, and divinity. The Greeks, with their mythologies and early philosophical thoughts, gazed upon the sky and began asking questions that would shape millennia. What are stars? What holds them up there? What is the universe made of? While many civilizations told cosmic tales through mythology, it was in ancient Greece that the seeds of scientific cosmology were first known. Figures like Thales of Miletus, Anaximander, and Aristotle proposed that the universe was not ruled by divine chaos, but by laws knowable, observable laws. Fast forward to our time, we're no longer limited to philosophical speculation. We've landed on the moon, sent rovers to Mars, and launched telescopes that peer into the earliest ages of the universe. From optical instruments to radio waves to gravitational wave detectors, we've transcended the limits of our senses, and yet, one question continues to captivate us above all. Where did it all begin? In this video, we explore the Big Bang Theory, the most widely accepted scientific explanation for the origin of the universe. We'll journey through evidence, physics, and the people who shaped our understanding of the cosmos. But first, if you're fascinated by astronomy, cosmic mysteries, and the science behind the stars, don't forget to subscribe and like this video. The universe is vast, but we'll explore it together one idea at a time. The Big Bang Theory, George Lemaitr's radical idea. For centuries, people believed the universe was static and eternal, unchanging, and infinite in all directions. Even Albert Einstein, in 1917, adjusted his general theory of relativity by inserting a cosmological constant lambda to keep the universe from collapsing under its own gravity. This assumption held until one radical idea challenged it all. In the 1920s, Georges Lemaitre, a Belgian priest, physicist, and astronomer, proposed something revolutionary. The universe is not static, it's expanding. And if it's expanding, it must have started from a single point. Lemaitre called this point the primeval atom, a cosmic egg that exploded and started the expansion of space and time. Though his proposal was met with skepticism, it was grounded in Einstein's own equations without the artificial constant. Ironically, Einstein initially rejected Lemaitre's idea, calling it abominable. Yet years later, Einstein would publicly praise Lemaitre, admitting that dismissing him was the biggest blunder of his career. But Lemaitre's theory remained a bold speculation until someone saw the universe moving. Edwin Hubble and the expanding universe. In 1929, American astronomer Edwin Hubble changed everything by observing the redshift of light from distant galaxies. He discovered that galaxies are moving away from us, and the farther they are, the faster they move. This relationship became known as Hubble's law, and it confirmed what Lemaitre had predicted. Hubble's observations provided the first empirical evidence that the universe was expanding. This implied that, if we reverse time, the universe must have once been compacted into an extremely dense and hot state. Thus, the idea of a cosmic beginning, later named the Big Bang Theory by Fred Hoyle, ironically as a term of mockery, began to gain traction. Irony aside, the name stuck. So, what is the Big Bang? The Big Bang was not an explosion in space. It was an explosion of space itself. There was no outside of it. Space, time, energy, and matter all emerged from the singular event about 13.8 billion years ago. At that moment, the universe was unimaginably hot and dense. In the first 10 seconds, it underwent a brief period of cosmic inflation, expanding exponentially. As it cooled, elementary particles like quarks, gluons, and leptons formed within minutes. Nuclear fusion created simple nuclei, hydrogen, helium, and trace amounts of lithium. This period is supported by nuclear astrophysics, especially Big Bang nucleosynthesis (BBN), which accurately predicts the observed abundance of light elements in the universe today. But to strengthen the theory even more, we need evidence of the actual glow left over from the Big Bang, and we found it by accident. The cosmic microwave background, echoes of the Big Bang. If the Big Bang really happened, it must have left behind some kind of trace, a cosmic fingerprint. That evidence came in the form of the cosmic microwave background (CMB), a faint glow of radiation that fills the universe. It's the oldest light we can see, dating back to when the universe was just 380,000 years old, a mere baby on cosmic timescales. The accidental discovery of the century. In 1965, Arno Penzias and Robert Wilson, to radio astronomers working at Bell Labs in New Jersey. We're testing a horn antenna for satellite communications. To their frustration, they kept detecting a persistent noise no matter where they pointed the antenna. After ruling out every possible interference, including pigeon droppings inside the antenna, they eventually realized they had stumbled upon the CMB, the afterglow of the Big Bang, exactly as predicted by theorists Robert Dick and Jim Peebles at Princeton. This serendipitous discovery earned Penzias and Wilson the 1978 Nobel Prize in Physics, and it cemented the Big Bang as the leading cosmological model. What is the CMB, really? The CMB is not just leftover heat. It's a snapshot of the universe at a time when atoms first formed, allowing light to travel freely through space. At that moment, the universe cooled enough to approximately 3,000 K for protons and electrons to combine into neutral hydrogen atoms. Light that was previously scattered in all directions could now travel unimpeded and has been doing so for nearly 14 billion years. Today, we detect this light as microwaves with a temperature of just 2.7 to 5 K, or about minus 170 C. It's incredibly uniform across the sky, but with tiny fluctuations just a few parts in 100. Zero that reflect early density differences in the infant universe. These fluctuations are the seeds of all cosmic structure, galaxies, stars, planets, even life. Precision measurements, WMAP, and planning to study the CMB in detail, scientists launched satellites. COBE 1989, NASA confirmed the black-body nature of the CMB spectrum. WMAP 2001 to 2010. NASA measured temperature fluctuations with exquisite precision. Planck 2009 to 2013. ESA provided the most detailed map of the CMB to date, revealing tiny anisotropies and refining our estimates of the age of the universe, approximately 13.8 billion years. The composition, approximately 68% dark energy, approximately 27% dark matter, 5% ordinary matter. The shape of the universe flat. On large scales, these missions confirm the predictions of the Big Bang Theory to astonishing accuracy. But even with all this evidence, some scientists still question, was the Big Bang truly the beginning of everything? Or could something have existed before it? The Big Bang Theory explains the evolution of the universe from a hot, dense state, but it leaves one profound mystery unanswered. What came before the Big Bang? For decades, the standard model of cosmology insisted nothing, time and space themselves were created in the Big Bang. Asking what came before is like asking what is north of the North Pole. But physicists are not so easily satisfied. Roger Penrose's conformal cyclic cosmology (CCC). In 2010, Sir Roger Penrose, Nobel laureate in physics, proposed a radical alternative. The universe didn't begin with a singularity, but is part of an eternal cycle of expansion and rebirth. This theory, called conformal cyclic cosmology (CCC), suggests that each eon cosmic cycle ends in a universe that expands infinitely. As it stretches, the difference between massive and massless particles disappears. This final state can be mathematically rescaled to conformal transformation into a new Big Bang, beginning the next eon. Evidence? Penrose and his collaborators claim to find Hawking points in the CMB circular patterns that may be relics from black hole evaporations in the previous eon. The idea is controversial, but Penrose's mathematical framework is rigorous, and it opens the door to a universe without a beginning. Ekpyrotic and cyclic models, brains colliding. Another bold theory comes from string theory, the ekpyrotic model, developed by Paul Steinhardt, Neil Turok, and others. In this scenario, our universe exists on a three-dimensional brain membrane floating in a higher dimensional space. Every so often, our brain collides with another brain, triggering a Big Bang-like event. The universe then evolves, expands, cools, until the next collision. This cyclic model avoids singularities and suggests a potentially infinite sequence of universes, each born from the destruction of the last. While speculative, these ideas are backed by high-level mathematics and M-theory, a branch of string theory that incorporates 11 dimensions. Bounce cosmology, no singularity required. Other physicists propose bounce models, where a previous universe contracted before bouncing into expansion. Key examples: loop quantum cosmology (LQC), pioneered by Abhay Ashtekar, uses quantum gravity effects to smooth out the singularity. In this view, time doesn't begin at the Big Bang, it simply continues through a quantum bounce. These models predict subtle features in the CMB polarization and gravitational wave background, which future telescopes like the proposed LightBird or CMBS-4 may detect. So does the Big Bang the beginning? In summary, the Big Bang marks the beginning of our observable universe, but not necessarily of everything. Modern physics is actively testing theories that propose a pre-Big Bang state, cyclic cosmic epochs, higher dimensional collisions, quantum bounces. Each theory pushes the limits of observation, but all share one thing: the universe may be far stranger and far older than we ever imagined. The fate of the universe, endless expansion or final collapse. Now that we've explored how the universe began, it's time to ask the next profound question: how will the universe end? This is not just a philosophical query, it's one rooted deeply in observational cosmology, theoretical physics, and thermodynamics. There are several scientifically plausible scenarios, and each one depends on the geometry, mass energy content, and expansion dynamics of the cosmos. The critical variable, density parameter omega. At the heart of the matter is the density parameter omega, a measure of how much mass energy the universe contains, compared to the critical density needed to halt its expansion. Omega greater than 1. A closed universe. Gravity eventually reverses expansion. Big crunch. Omega equals 1. A flat universe. Expansion slows, but never quite stops. Omega less than 1. An open universe. Expansion continues forever. Observations from missions like WMAP and Planck suggest omega is very close to 1, meaning our universe is flat. With a twist, dark energy is accelerating expansion. Scenario 1. The heat death. Most likely, based on current evidence, the most accepted fate is the heat death, also called the Big Freeze. Driven by dark energy, the universe continues to expand at an accelerating rate. Galaxies drift apart, stars burn out, and black holes evaporate via Hawking radiation. Entropy increases until all usable energy is exhausted. The universe becomes cold, dark, and lifeless, a sea of low-energy photons and subatomic particles. Timeline: stars stop forming. Approximately 100 trillion years. Black holes evaporate. Approximately 10 years. Proton decay, if it occurs, approximately 10 years. This feature is supported by measurements of type Ia supernovae and the cosmological constant lambda. Scenario 2. The Big Rip. If dark energy is not constant but instead increases over time, a form of phantom energy, then the expansion will accelerate to catastrophic levels. Predicted by Robert Caldwell in 2003, the Big Rip scenario says, in approximately 20 billion years, galaxies, stars, planets, and even atoms will be ripped apart by expansion. Space-time itself could tear apart at the singularity. This scenario is mathematically consistent with some models of dynamic dark energy, but current data favors a cosmological constant. Scenario 3. The Big Crunch. Now less likely, this is the reverse Big Bang scenario. Gravity eventually overcomes expansion. The universe slows, stops, and collapses inward. Temperatures soar as galaxies and stars converge into a final, hot, dense singularity. The Big Crunch would be followed potentially by another Big Bang in a cyclic fashion. But current observations show the universe's expansion is accelerating, not decelerating. So unless dark energy reverses or decays, the Big Crunch appears unlikely. Scenario 4. Vacuum decay. The quantum wild card. The most terrifying possibility is rooted in quantum field theory, vacuum metastability. If our universe is in a false vacuum, a local minimum in the Higgs field, a quantum tunneling event could shift it to a true vacuum, destroying physics as we know it. Proposed by theorists like Sidney Coleman, this bubble of death would expand at light speed, instantly rewrite all fundamental forces, and obliterate matter and life. This doomsday would arrive without warning, but it's only theoretical for now. What are cosmologists doing about this? A lot. Dark energy surveys like DESI, Euclid, and the Nancy Grace Roman telescope aim to pin down the nature of dark energy. Gravitational wave detectors may reveal signs of black hole mergers that shape the universe's evolution. Quantum gravity models could explain what happens in extreme end-of-universe scenarios. In short, the fate of the universe hinges on the true nature of dark energy, the behavior of quantum fields, and whether gravity itself changes at large scales. Whether it ends in a whisper or a bang, one thing is certain: the cosmos is a story still unfolding, and we're just beginning to read its final chapters. Echoes from the beginning. The cosmic microwave background. If the universe began with a massive explosion, the Big Bang, then surely it must have left behind a trace, and indeed it did. This ancient remnant, known as the cosmic microwave background (CMB), is the oldest light in the universe, and it offers some of the most compelling evidence for the Big Bang theory. What is the CMB? The CMB is faint microwave radiation that fills all of space. It's the afterglow of the universe when it was just 380,000 years old. A baby compared to its current age of 13.8 billion years. Before this time, the universe was hot, dense, opaque because photons were constantly scattered by free electrons. But as the universe cooled below approximately 3000 K, electrons combined with protons to form neutral hydrogen. This moment, called recombination, allowed photons to travel freely, creating a snapshot of the infant universe. This snapshot is what we now detect as the cosmic microwave background. How was it discovered? The discovery of the CMB in 1965 by Arno Penzias and Robert Wilson was accidental. Working at Bell Labs, they were calibrating a radio antenna when they detected a persistent noise from every direction. They thought it was interference. It wasn't. That noise turned out to be the thermal remnant of the Big Bang predicted to decades earlier by George Gamow, Ralph Alpher, and Robert Herman in the 1940s. This discovery earned Penzias and Wilson the 1978 Nobel Prize in Physics. What does the CMB tell us? The CMB is not perfectly uniform. They reveal density variations in the early universe, which seeded the formation of galaxies and large-scale cosmic structures. These tiny ripples are imprints of quantum fluctuations, stretched across space during cosmic inflation, COPE, WMAP, and Planck. The CMB mission timeline. Over the past 30 years, several satellite missions have mapped the CMB in increasing detail. COBE 1989 to 1993, first to detect the tiny anisotropies in the CMB. WMAP 2001 to 2010 provided precise measurements of the universe's age, composition, and curvature. Planck 2009 to 2013 delivered the most detailed map of the CMB to date, resolving temperature differences down to microkelvin levels. These missions confirmed the universe is 13.8 billion years old, composed of approximately 5% baryonic matter, 27% dark matter, and approximately 68% dark energy, spatially flat on large scales. The CMB power spectrum, a cosmic fingerprint. By analyzing the angular power spectrum of the CMB, cosmologists extract a wealth of data about the total density of the universe, omega_total, the curvature of space, the ratio of baryonic matter to dark matter, the expansion rate Hubble constant, and even the nature of primordial gravitational waves. It's like reading DNA, only it's the genetic code of the universe. Open questions. Despite its success, the CMB still leaves open questions. Why is the CMB so uniform across vast distances, even beyond causal connection? This inspired the theory of inflation. What caused the initial fluctuations? Why is the Hubble tension, the disagreement in expansion rates, still unresolved? These are the next frontiers in cosmology. The cosmic microwave background is not just a relic of the past, it's a cosmic Rosetta Stone, helping decode the earliest moments of our universe and guiding us into the future of astrophysics. Inflation, the fastest second in the universe's history, in the earliest moments after the Big Bang. We are talking about a fraction of a second. Something astonishing may have happened. The universe expanded faster than the speed of light. This isn't science fiction. It's a widely accepted theory in modern cosmology known as cosmic inflation. What is inflation? Inflation is the idea that the universe underwent a period of exponential expansion in the first 10 to 10 seconds after the Big Bang. During this unimaginably short time, the universe grew in size by a factor of at least 10, transforming from subatomic to macroscopic scales. Imagine something the size of a proton suddenly ballooning to the size of a galaxy in less time than it takes light to cross an atom. This is not a violation of Einstein's relativity. Special relativity prohibits objects from moving through space faster than light. But space itself can expand at any speed, and during inflation, it did. Why was inflation proposed? The inflationary model was proposed by physicist Alan Guth in 1980 to solve several puzzles left unexplained by the classical Big Bang theory, the horizon problem. Why is the universe so uniform in all directions even though distant regions were never in contact? The flatness problem. Why is the universe's geometry so close to flat, when even slight curvature would have grown over time? The monopole problem. Where are the magnetic monopoles predicted by grand unified theory's guts? Inflation provides elegant solutions to all three. How does inflation solve these? Horizon problem. Before inflation, all regions were in thermal contact and reached equilibrium. Then, inflation stretched them beyond each other's horizons. So what we see as causally disconnected regions were once neighbors. Flatness problem, rapid expansion flattens spacetime. Just like inflating a balloon flattens a small patch of its surface, monopole problem, inflation, dilutes any relics like monopoles to undetectable levels. In short, inflation resets the initial conditions of the universe in a way that matches what we observe today. Experimental clues supporting inflation. While we cannot directly observe inflation, it occurred before light could travel. There are observable consequences: quantum fluctuations, structure formation. Tiny quantum fluctuations during inflation were stretched to cosmic scales and seeded the large-scale structure of the universe: galaxies, clusters, and voids. CMB anisotropies. The pattern of temperature fluctuations in the cosmic microwave background matches predictions from inflationary models with remarkable accuracy. Primordial gravitational waves still being searched for. Inflation should have created a background of gravitational waves ripples in spacetime, which could leave B-mode polarization signatures in the CMB. Experiments like BICEP2, Planck, and the upcoming Lightbird mission are focused on detecting these signatures, variants, and theoretical advances. Since Guth's original proposal, inflation theory has evolved. Variants include chaotic inflation. Andre Lind, inflation begins in random quantum fluctuations. New inflation. Inflation arises from a slow-rolling scalar field called the inflaton. Eternal inflation. Some regions of space continue inflating forever, potentially giving rise to a multiverse, though the details are debated. Inflation remains a cornerstone of modern cosmology. Is inflation the final answer? Not necessarily. Some physicists propose alternatives like ekpyrotic models from string theory and brane cosmology, loop quantum cosmology, or cyclic universe models, but none of these has yet provided better agreement with observations than inflation. As Stephen Hawking once said, inflation is the only model that explains why the universe looks the way it does. Cosmic inflation is the spark that shaped our universe, smoothing it, flattening it, and seeding it with the potential for stars, galaxies, and ultimately, life. The birth of elements, primordial nucleosynthesis, and the first stars after the cosmic inflation ended. The universe kept expanding, but at a slower pace. As it expanded, it cooled. Roughly 1 second after the Big Bang, the universe was about 10 billion degrees Kelvin, still unimaginably hot, but cool enough for subatomic particles to begin forming stable structures. This ushered in one of the most critical phases in cosmic history, Big Bang nucleosynthesis (BBN), the formation of the first atomic nuclei. What is Big Bang nucleosynthesis? Big Bang nucleosynthesis is the process that formed the first light elements in the early universe. It occurred during the first 3 minutes after the Big Bang, when conditions were just right, hot, and dense enough for nuclear reactions, but cool enough to allow protons and neutrons to bind. During this period, most of the matter in the universe was in the form of hydrogen nuclei, single protons, deuterium, a proton and a neutron, helium-3 and helium-4, and trace amounts of lithium-7 and beryllium. No heavier elements formed. The universe wasn't hot or dense enough for that. Heavier nuclei had to wait until the first stars were born. How do we know this happened? The predictions of BBN match our observations extraordinarily well. About 75% of the baryonic mass in the universe is hydrogen, about 25% is helium-4, and tiny traces of deuterium, helium-3, and lithium-7 are observed in ancient gas clouds. These ratios are consistent with what BBN predicts for a universe that expanded from a hot, dense state in 2003. Data from NASA's Wilkinson Microwave Anisotropy Probe WMAP confirmed the abundance of light elements match predictions, solidifying BBN as a central piece of Big Bang cosmology, the cosmic dark ages. After nucleosynthesis, the universe continued to cool. For the next 380,000 years, it remained a hot soup of ionized hydrogen and helium, a plasma. Light couldn't travel freely. Photons constantly scattered off free electrons. This era is known as the cosmic dark ages. Only when the universe cooled to around 3000 K, electrons combined with nuclei to form neutral atoms in a process called recombination. This moment when the universe became transparent gave birth to the cosmic microwave background. Radiation. We talked about that earlier. The first stars is cosmic dawn. But how do we go from a foggy, neutral gas to stars, galaxies, and planets? It started with tiny density fluctuations imprinted by inflation, which served as seeds for gravitational collapse. Over hundreds of millions of years, These fluctuations grew into clumps of matter. Around 100 to 300 million years after the Big Bang, the first stars ignited a period known as the cosmic dawn. These population 3 stars were unlike anything we see today. They were enormous, 100 to 300 times the mass of the Sun, composed entirely of hydrogen and helium, with no heavy elements called metals. In astronomy, short-lived and incredibly hot. When they died, they exploded as hypernovae, enriching the cosmos with the first heavy elements carbon, oxygen, nitrogen, iron. These elements became the building blocks of everything: planets, DNA, oceans, and us. How do we study the first stars? We can't see them directly yet, but we detect their fingerprints. James Webb Space Telescope JWST is already pushing the frontier, imaging galaxies formed only 100 million years after the Big Bang. Future telescopes like the 30-meter telescope TMT and extremely large telescope belt aim to resolve even earlier objects. We also detect ancient stars in the halo of our own galaxy, low metallicity stars that may be descendants of early stellar generations. Cycle of matter begins. From this moment forward, the cosmic recycling program began. Stars formed, burned their fuel, exploded, spread heavy elements, and new stars formed from enriched gas. This process continues today. Every atom of carbon in your body was forged inside a dying star. As astronomer Carl Sagan famously said, "We are made of star stuff." This phase from nucleosynthesis to the first stars transformed the universe from inert hydrogen gas into a dynamic, structured cosmos. The formation of galaxies and cosmic structure from chaos to order, with the first stars lighting up the cosmos. The next monumental transformation was underway, the formation of galaxies in the large-scale structure of the universe. But how did random clumps of gas and dark matter evolve into the billions of galaxies we observe today? To understand that, we need to look at the invisible scaffolding of the cosmos. The role of dark matter, the cosmic web. Although normal matter, protons, neutrons, and electrons makes up everything we can see, it only accounts for about 5% of the universe's total content. Another 27% is dark matter, mysterious substance that doesn't emit or absorb light, but exerts gravitational influence. The rest is dark energy, which we'll return to later. Early in the universe's history, dark matter began clumping together under the pull of gravity, forming dense regions known as dark matter halos. These halos served as gravitational wells into which normal matter, baryonic matter, could fall and condense. This structure, an enormous interconnected network, is what scientists call the cosmic web. It consists of filaments of galaxies, vast voids of empty space, and massive clusters of dark matter and galaxies at the intersections. The formation of galaxies. As baryonic matter collapsed into the gravitational wells of dark matter halos, it began to heat up and form rotating disks of gas. In the densest regions, gas cooled and fragmented into stars. Over time, these stellar nurseries evolved into galaxies. There are several types: spiral galaxies like our Milky Way with rotating arms, elliptical galaxies large, featureless, often resulting from collisions, irregular galaxies smaller, chaotic structures. The formation and evolution of galaxies is a complex dance involving gas dynamics, star formation, supernova feedback, and galactic mergers. Simulating the cosmic web, you might wonder, how do we know all this? The answer lies in cosmological simulations, powerful computer models that replicate the evolution of the universe. One of the most famous is the illustrious simulation 2014, followed by the even more detailed illustrating project 2018. These simulations start with conditions shortly after the Big Bang, include dark matter, baryonic matter, gravity, magnetism, and hydrodynamics, and evolve the universe forward for 13.8 billion years. The result? A strikingly accurate reproduction of the observed cosmic web and galaxy distribution. These simulations match real astronomical surveys like the Sloan Digital Sky Survey, SDSS, giving scientists high confidence in our models. Observational evidence. On the observational side, deep field images from telescopes like the Hubble Space Telescope and James Webb Space Telescope JWST have revealed thousands of galaxies in tiny patches of sky. Some formed just 100 million years after the Big Bang. These findings confirm the timeline of structure formation and support our understanding of the hierarchical formation model. Small structures formed first, then merged to build larger ones. Feedback mechanisms, supernovae, and black holes. As galaxies grew, they were shaped by feedback mechanisms. supernova explosions from massive stars sent shockwaves through interstellar gas, regulating star formation. Supermassive black holes at galactic centers ejected powerful jets of energy, known as active galactic nuclei (AGN), which could suppress or trigger new star formation. These processes help determine a galaxy's shape, size, and fate. Without feedback, simulations produce too many stars, too fast diverging from reality. Feedback, as it turns out, is crucial to cosmic balance. Our place in the cosmic structure. Our own Milky Way galaxy is part of the small group of galaxies known as the Local Group, which also includes the Andromeda Galaxy, the Triangulum Galaxy, and dozens of dwarf galaxies. The Local Group is itself part of a larger structure, the Laniakea supercluster, which spans over 500 million light-years. This hierarchical structure galaxies, clusters, superclusters is the result of billions of years of cosmic evolution, all seeded by tiny fluctuations in the early universe. From quantum ripples to majestic galaxies, the universe has assembled itself into a grand cosmic architecture, and all of its stars, planets. Life rides on the invisible backbone of dark matter. Dark energy in the accelerating universe, the future of everything. Just when cosmologists thought they had a good grasp of how the universe works, the cosmos threw them a curveball, one that would rewrite the story of cosmic destiny. Until the late 1990s, scientists believed that the expansion of the universe, first discovered by Edwin Hubble, would eventually slow down due to the pull of gravity. But then something astonishing happened, the discovery that shocked cosmology. In 1998, two independent teams of astronomers, the Supernova Cosmology Project and the High Z Supernova Search Team, made a discovery that stunned the scientific world. By observing distant Type Ia supernovae, which act as standard candles, objects of known brightness, the teams found that these exploding stars were dimmer than expected. This meant they were farther away than they should be in a decelerating universe. They're shocking. Conclusion: the expansion of the universe is not slowing down, it's speeding up. The leaders of these teams, Saul Perlmutter, Brian P. Schmidt, and Adam G. Rees, were awarded the 2011 Nobel Prize in Physics for this groundbreaking discovery. Enter dark energy. To explain this accelerating expansion, scientists proposed a new component of the cosmos: dark energy. Dark energy is a repulsive force counteracting gravity. It accounts for a staggering 68% of the universe's total energy content. But here's the kicker: we have no idea what dark energy actually is. It could be the cosmological constant lambda Einstein introduced and later rejected, a new field permeating space called quintessence, or something even more exotic, a property of vacuum energy or the fabric of space-time itself. Observational evidence. The evidence for dark energy comes from multiple, independent lines of observation. Supernovae, as discussed, their dimness revealed accelerated expansion. Cosmic microwave background (CMB) data from WMAP and Planck satellites confirm a flat universe. That requires dark energy to balance its geometry. Baryon acoustic oscillations bow large-scale galaxy distributions show patterns consistent with dark energy's influence. All signs point to the same conclusion: the expansion of space itself is accelerating. What does this mean for the long-term future of the cosmos? Depending on the nature of dark energy, there are several possible outcomes. 1. The Big Freeze, most likely. If dark energy remains constant, the universe will continue to expand forever. Galaxies will move farther apart. Stars will burn out. Black holes will evaporate via Hawking radiation. And the universe will approach a cold, dark, and empty state known as heat death. 2. The Big Rip. If dark energy's repulsion increases over time, it could eventually overcome all other forces. First, galaxies would be torn apart, then solar systems, then atoms themselves, ending in a dramatic ripping apart of space-time. 3. The Big Crunch, Big Bounce. If dark energy weakens or reverses, gravity could win. The universe would collapse in on itself, possibly leading to a new Big Bang, a cyclic universe model supported by some quantum gravity theories. Currently, the data most strongly supports the Big Freeze scenario, but the exact nature of dark energy remains one of the biggest open questions in physics. Where we go from here? Understanding dark energy is now a top priority in astrophysics and cosmology. Projects like the Euclid Space Telescope by ESA, launched 2023, NASA's Nancy Grace Roman Telescope scheduled for 2027, and the Dark Energy Survey are all designed to map out how cosmic expansion has changed over time, helping us constrain the nature of dark energy. Even the James Webb Space Telescope may indirectly contribute by examining early galaxies and providing better cosmological models. Solving the dark energy puzzle could lead to a revolution in physics, much like quantum mechanics or relativity, and may even unlock a unified theory of the universe. As we look to the stars, we're not just seeking knowledge, we're uncovering the ultimate fate of existence itself. And in this vast cosmic mystery, we are not merely observers, we are part of the story. What came before the Big Bang? Hypotheses beyond the observable universe. The Big Bang Theory provides a robust explanation for the evolution of our universe from a hot, dense state about 13.8 billion years ago. But there is one question that has haunted both scientists and philosophers alike. What came before the Big Bang? This isn't just a scientific question, it's a philosophical challenge. A riddle that tests the very limits of human understanding and the nature of time itself. Was there a before? According to general relativity, space and time are intertwined into a four-dimensional fabric called space-time. The Big Bang wasn't an explosion in space. It was an expansion of space and time itself. This means that asking what came before the Big Bang is like asking what is north of the North Pole. By some interpretations, time itself began at the Big Bang. There was no before. But theoretical physicists, never satisfied with simple answers, have proposed bold alternatives. Hypothesis 1. The cyclic universe. One possibility is that the Big Bang was not the beginning, but simply a transition in an eternal cycle of birth and death. This idea is central to the conformal cyclic cosmology (CCC) proposed by Sir Roger Penrose, Nobel laureate in physics 2020. According to CCC, the universe undergoes cycles, or eons. Each eon begins with a Big Bang and ends in a stretched, cold, empty state. The smooth, scale-invariant geometry at the end of one eon becomes the seed for the next. Penrose even claims to have found evidence in the cosmic microwave background (CMB), concentric rings of low temperature variation that may hint at events from a previous universe. Hypothesis 2. Quantum gravity and the bounce. Another idea comes from loop quantum gravity, a theory that attempts to unify general relativity and quantum mechanics. According to work by physicists like Martin Biold, space and time are quantized, made up of discrete chunks. In this model, instead of a singularity, a point of infinite density, the universe bounces from a prior contracting phase. There was a previous universe, which collapsed. Then, quantum gravity effects triggered a big bounce, creating our current expansion. This theory removes the singularity, replaces it with a minimum volume, and provides a mathematical framework for a pre-Big Bang state. Hypothesis 3. The multiverse. A third idea stretches our imagination even further. It's the multiverse. Some versions of inflation theory, particularly eternal inflation proposed by Andre Lind, suggest that our universe is just one bubble in a vast multiverse. Quantum fluctuations can cause regions of space to undergo inflation at different times. Each bubble becomes a universe with its own laws of physics. New universes are constantly being created, possibly without end. In this scenario, the Big Bang wasn't the beginning of everything, just the beginning of our local patch of a much larger, eternal multiverse. Why it's so hard to know? These ideas are theoretically fascinating, but testing them is extremely difficult. We can only observe as far as 13.8 billion light-years, limited by the cosmic horizon. Anything before the Big Bang or outside our universe lies beyond direct observation. This doesn't stop scientists from trying. Experiments like LISA, Laser Interferometer Space Antenna, may detect primordial gravitational waves from the earliest instance of the universe. Advances in quantum gravity and string theory may provide clues. Still, at the cutting edge of cosmology, science starts to resemble metaphysics, where equations describe possibilities, but data is elusive. So what came before the Big Bang? Was it a previous universe, a quantum bounce, an eternal multiverse? Or was it truly the origin of time itself? We don't have the answer yet, but that's what makes cosmology so deeply human. In trying to understand the universe, we confront our own limits and our boundless curiosity. As Nobel-winning physicist Frank Wilczek once said, the universe is not only stranger than we imagine, it is stranger than we can imagine. And that, dear viewers, brings us to the end of our journey through the beginning of everything, from ancient stargazers to Nobel laureates. From primordial explosions to hypothetical multiverses, we've traveled far. If you found this exploration thought-provoking, be sure to subscribe to this channel for more deep dives into the cosmos. Like and share this video to keep the curiosity alive. Comment below with your favorite theory or your wildest guess about what came before the Big Bang. Until next time, keep looking up because the universe is not done telling its story.